Opamp nonlinear applications. Nonlinear applications. Very interesting. This I have already told you in the very beginning when we started our discussion on op-amp circuits. Linear integrated circuits. The very name itself is LIC and application. Linear integrated circuits and applications. And having said that, we have also seen some of the basic parameters related to the operational amplifier. Then we started with the feedback, right? And so far whatever we have discussed in these many classes, whatever we have engaged, right? So we have all seen the applications of the operational amplifier in the linear region, right? When I say that linear region, right, where the response is directly proportional to the excitation. This is what you have studied as long as a linear circuit is concerned, right? Whereas when I talk about the non-linear circuits, right, where your response need not necessarily be proportional to the excitation, and here basically we call these things as switching circuits. Suddenly something gets switched to some value, right? So which is definitely not linear. So whenever you have the diode characteristics, right, whenever you have got your other transistor characteristics and all, they are not linear, right, where your response need not necessarily be proportional to the excitation, right? So that such kind of applications we will have to see here in the non-linear circuits, right? And whenever I speak about the operational amplifier, when I have something like this, some input I am giving, and this is my VCC minus VEE, right? So suppose if I give the input to the non-inverting terminal, right, and if I consider this terminal to be grounded, let me say that this is my input, right? So now this is the basic circuit from where we have started all our discussions, right? Afterwards we slowly started to have some kind of feedback with some element, right? Could it be resistor, capacitor, or the combination of that, because of which we could realize so many other circuits. In all those circuits we found that the response is directly proportional to excitation. That is the reason why we called them as the linear circuit, right? Now whenever we speak about the nonlinear circuit, or which we also call it as the switching circuit, the feedback matters here, right, in order to have the nonlinear circuit, right? Either you have no feedback, or you have positive feedback. This is a very important point to be noted, right? Because you even sometimes me also, right? So nobody is an exception, right? Whenever you start drawing some circuit, we make some very fundamental mistakes, elementary mistakes, right? If your basics are clear here, right, your understandings are clear, you would not do that, right? So whenever you take any linear applications, most of the linear applications, I'll always have the negative feedback. But whenever you go into the switching part of the operational amplifier, either you will have no feedback or you will have the positive feedback. This is a very important point to be noted, okay? So now with this as the background, right, with this as the background, we will now try to have some of the fundamentals, right? So let me quickly go through the syllabus content where we have to study about the comparators, right? So comparators means you have already studied about the digital comparator, A less than B, A equal to B, A greater than B, 1-bit comparator, how exactly you get the output for different conditions fulfilled there, right? We have something called as Schmidt trigger, right? I don't know whether you have heard about this word or not in analog electronics. Have you heard about the word Schmidt trigger? Schmidt trigger circuits?
Yes, sir.
Okay. Basically, they are the waveform generators, right? Anyway, we will go into the details of all those things. Monostable multivibrators, definitely you must have heard about this, right? Then you go to the other category like oscillators, right? Triangular waveform generator, RC phase shift oscillator, Wien bridge oscillator, right? And then again you go with one more category, that is the filters, active filters, right? Wherein you will have to study about the second order Butterworth low pass filters, high pass filters, band pass filters, and band elimination filters in this particular topic, where all these things whatever I have mentioned so far, they are considered as the non-linear circuits or the applications of non-linear circuits. Whenever I talk about the non-linear circuit, basically they are the switching circuits where your response is not proportional to the excitation. But having said that, whenever we deal with the non-linear circuits, your operational amplifiers, the switching circuits, will have to fulfill certain important conditions or certain criteria to be fulfilled, right? We will try to take those things first. Conditions, as long as the non-linear circuits are concerned. Let me take the first one. You will come to know this is very simple. First one is called as the output voltage swing. Output voltage swing. Now, whenever I speak about the switching circuits, okay, whenever I speak about the switching circuits, to what values the output is going to switch, right? Or between what values the output is going to switch. What decides the switching of the output to what value? All those things are supposed to be known to us very clearly, right? So the switching generally takes between positive and negative saturation values. You know what exactly we mean by the saturation values, right? So when we have this, right, the plus V sat or V naught sat you can take, right? Many a times this word we will be using here in our switching applications, right? So this plus V naught sat will be generally equal to VCC minus 1, and minus V naught sat will be generally equal to minus VEE plus 1. That means whenever the output switches or the output swings between the two values, something like this, please see now I have gone into output which is a pulse in shape or rectangular in shape, right? So now this is called as plus V naught sat and this is called as minus V naught sat if you consider this waveform, right? What values are those plus V naught sat and minus V naught sat means? That depends upon these. You can see here plus VCC and minus VEE. Suppose if your operational amplifier is say working with plus 12 volts here and minus 12 volts, so this will be 11 volt because it is VCC minus 1. This will be minus 11 volt, minus VEE plus 1, minus 12 plus 1, minus 11 volt, right? So what is the indication here? It is not necessary and it is not possible for us to have the output swing between plus VCC and minus VEE, because you know that the operational amplifiers are having the internal stages. You have got the operational amplifiers with transistors and all. We have already discussed about those things. There will be certain voltage drop taking place within the operational amplifier, because of which it may not be possible for us to have the output swing to the extent of the supply voltage values. Generally it will be as a thumb rule, it will be considered as plus 1 volt and minus 1 volt of the supply voltages. This is one point to be noted, right? So that is the output voltage swing. So in so many occasions we will come across these things later. Then let us now look into the second aspect. The second aspect, after having seen the output voltage swing, this second aspect deals with when exactly the output will swing from minus V naught set to plus V naught set and plus V naught set to minus V naught set. This is another important point to be noted. That is the input voltage range for switching. Input voltage range for switching, right? So now if you look at this diagram, we apply some voltage here, right? And we have got, of course, the other voltage as 0. So therefore solely this voltage will decide in between what values the output switching takes place, right? So this input voltage level we are trying to find out here, right? Input voltage range for the output to swing. So that we generally take the minimum differential voltage, minimum differential voltage required for the output voltage swings. Minimum differential voltage required for the output voltage swing is given by the formula approximately, okay, this is VCC divided by M. You know what exactly is the M? M is the open loop gain. Now you will have the answer for this numerically. I will tell. Suppose if you consider, say you have for IC 741, your M value is 50,000 approximately, and if your VCC, let us say if your VCC is 15 volts, okay, if your VCC is 15 volts, then your VI diff will be 15 divided by 50,000. This is an example, okay, it doesn't account to any calculation and all. Now if I am having an operational amplifier which is IC741, which works with plus or minus 15 volts, and if you consider its open loop gain as say 50,000, so now 15 divided by 50,000, can somebody tell me? So this is plus or minus 15 divided by 50,000, 5 3s are, so 300 microvolt. Am I right?
Yes, sir.
Okay. So now please look here. If you
Yes, sir. No.
yeah, if you consider a voltage here of the input voltage of say 300 microvolt, so 300 microvolt is a very small voltage, right? So that means it is almost at zero level only. Ideally speaking, it should be zero only as per the requirements of an ideal operational amplifier is concerned, because your M is infinite there, right? When M is infinite, your V differential input voltage should be zero. But if you consider some finite high value of the input, the open loop gain, then it is coming here as about 300 microvolt. For such a small change in the input voltage from 0 to 300 microvolts on the positive side, the output swing takes place between minus V naught C sat to plus V naught sat, provided we assume that the initial output is at minus V naught sat. Then again, whenever the input goes to the negative side here, right? So here let us say that this is my input, something like this, with such a small input of about 300 microvolt on either side, the output will switch from its previous state to the next state. So this is another important point to be noted as long as the input voltage swing or the range is concerned, right? So this is second criteria or the second parameter which we are supposed to take, and the third parameter sorry, is the slew rate. We have already seen about the slew rate, right? So what is slew rate? Delta V naught divided by delta T. We have already taken. So it is the time required for the input voltage to reach its maximum, right? So now this delta T, we are taking it as delta V naught divided by S. This is a very another important parameter. The rise and fall time of the operational amplifier is definitely related to its slew rate. We have already seen this, right? So therefore, in order to have the proper output swing, right? So suppose now I want to have the output swing something like this. This is my perfect output swing. But instead, okay, when the input is like this, you may end up in getting the output something like this. We have already seen the slew rate limited amplitude, slew rate limited frequency and other things, right? We don't expect the output swing to be like this. We want the output swing to be like this, a perfect square wave, right? So therefore, this is another parameter wherein the rise and fall time of the operational amplifier input waveform, it should be much smaller than the pulse width. At the rise and fall time of the input waveform or the signal should be at least instead of writing this, should be less than 10% of the total pulse width. We will see these things, right? We will take one example and we will see later, right? So the distortion, in order to avoid the distortion at the output, or in order to avoid the waveform other than the perfect square waveform, right? So you will have to have the rise and fall time of the input waveform which should be at least less than 10% of the total pulse width. These are the three parameters or the three criteria to be considered as long as the switching applications of the operational amplifiers are concerned, right? So with these backgrounds, we will now try to go into some of the simple applications as long as the comparators are concerned, right? So we will there are so many configurations. You can have n number of configurations depending upon requirement. So it's not necessary and possible for us to discuss each and every combination. We will see some of the key configurations, and after having the idea about these things, you should be able to write any kind of circuit you want depending upon your understanding, right? So now the first one here is zero crossing detector. So you know what exactly is a zero crossing detector, right? So we have probably studied these things in your analog electronic circuits also. Now when I have, say, an input signal like this, in this one complete cycle, how many occasions does the waveform cross 0? 1, 2 and 3, and afterwards of course it repeats, correct or not? So every time the input crosses 0, it should be detected. So how do you detect it? by some kind of the output status or the output values, right? So now here I can have a zero crossing detector output something like this. I will draw the output also on the same frame so that you can easily understand this. It will be something like this, right? So please draw both the waveform of the same size. Maybe here I have not drawn it like that. So this is my V0, and again needless to mention that this is plus V0 sat and this is minus V0 sat, something like this, and this is my input signal. This is how your output of a zero crossing detector should look like. Now how do you draw the circuit for this? Can anyone? It is the same circuit which I had drawn previously here in this frame. This itself is your zero crossing detector. We will see how exactly it is so, right? So now here I have one op-amp. I am giving the input to my non-inverting terminal, and the inverting terminal straight away I will ground it. So this is my plus VCC and this is my minus VEE and this is my V0. That's all. I don't use any feedback here, right? That is the reason why. So whenever the input is above the differential voltage, so if I take the previous example, say 300 microvolt, if you assume that I have taken a similar operational amplifier with the characteristics which I have shown in the previous slide, then whenever the input goes above 300 microvolt from initial minus V0 sat, so the output will now swing to plus V0 sat from here to here, and as long as your input is greater than plus 300 microvolt or VID differential voltage, the output will remain in plus V0 sat only. Once your input crosses zero, ideally speaking, practically speaking 300 microvolt in the previous case, so your output will go from plus V0 sat to minus V0 sat, and it will remain in minus V0 sat as long as your input is less than minus 300 microvolt. So or it is less than zero, strictly ideally speaking. In this way you get the continuous square wave generation here. We can use this for some other purpose also, but in this context I am talking about the zero crossing detector. So every time the input goes to a zero, your output status is going to change, or it swings between plus V0 sat and minus V0 sat, right? So if V in is greater than V reference, in this case my V reference is 0, right? V0 is equals to plus V0 sat. If your V in is less than V reference, or in this case it is less than 0, your V0 is equals to minus V0 sat. And you again need not mention that your V0 sat plus or minus V0 sat is equals to plus or minus VCC plus or minus or minus plus 1, like this we can take. We have already seen this, right? This is the zero crossing detector, simple zero crossing detector. All of you are able to understand this or not? This is basically a comparator only. We are comparing it with 0 volt, or we are comparing it with a reference which is equals to 0 here. Now, is it over?
Yes, sir.
Okay. So now let me take non-inverting type ZCD. Yes, non-inverting type ZCD. Initially, sorry, we have already taken about the non-inverting type. Now we will take about the inverting type of ZCD. Inverting type of ZCD. So, what changes you will make? Very simple. Again, you give the input to the inverting terminal, non-inverting terminal is grounded. That's all. V in, this is going to be your V0 plus VCC minus VEE. So now you know how would you draw the waveform. Suppose if I take the input signal something like this, yes, your output would look something like this. These things you should be able to realize very quickly. So this is plus V0 sat and this is minus V0 sat. This is my V in and this is my V0. This is as simple as this, the inverting type of zero crossing detector. If V in is greater than V reference, V0 is equals to minus V0 sat here. If V in is less than V reference, V0 sat, V0 is equals to plus V0 sat. Is that fine? All of you are able to understand this?
Yes, sir.
Okay. Only few students are replying, very few, always. Okay. So now we will try to look at one simple example to endorse the discussions which we have made in our previous slide. So what I would do here is, yeah, I will take it like this. Please note down, an inverting ZCD, an inverting zero crossing detector employs IC 741. An inverting ZCD employs IC 741 with plus or minus 12 volts supply. An inverting ZCD employs IC 741 with plus or minus 12 volts supply. Determine the typical output swing determine the typical output swing and the input level above which or above and below which, because both the sides the swinging takes place, right? uh, Input level above and below which the output swing takes place. Output swing takes place. Also calculate the rise time of output voltage. Also calculate the rise time of the output voltage. Very simple example. Everybody should be able to do on your own. Some of the answers you can directly tell, not necessary that you need the calculators. The first one, the output voltage swing. An inverting ZCD employs IC741 with plus or minus 12 volt supply. Determine the output voltage swing and the input level above and below which the output swing takes place. Also calculate the rise time of the output voltage. So what is the output voltage swing? Plus V naught sat is equals to plus VCC minus 1. So therefore it is plus 12 minus 1, that is plus 11 volt. Here I will be little elaborative, right? But later we take these things for granted. We go with the values quickly. So minus VEE plus 1, that is minus 12 plus 1 minus 11. So these need not be calculated. You can, when the supply voltage is plus or minus 12 volts, your output swing will be plus or minus 11 volts, that you can take for granted, right? So this is one thing. The second value what you need to take here is the input voltage that creates output swing, VID, which is approximately equal to, we had taken one formula earlier. What is VID equal to? You have
VCC by M.
Yes, VCC by M. At least some of you are noticing these things. This is 12 divided by M. It is IC741. So these things will not be given. M you can take it as 50,000. Okay. M you can take as 50,000. Can somebody calculate and tell me these values? Twelve divided by 50,000 amounts to how much?
240 microvolts, sir.
240 microvolts. 240 microvolts. Good. Second part is over. Now the third part, that is the rise time. Delta T is delta V naught divided by S. Delta T is equals to delta V naught divided by S. Please calculate. you have to take the slew rate. Delta V naught will be 11 plus 11, 12, 22 volts. So slew rate is how much? 0.5 volts per microsecond. Am I right? For your IC741?
Yes, sir.
Okay. 22
Yes.
divided by 0.5 volts per microsecond, or how do you take this? 0.5 into 10 to the power of 6 volts per second, right? Please calculate this. This is 0.5 into 10 to the power of 6 volts per second. So therefore here I will have to substitute 0.5 into 10 to the power of 6.
44 microsecond.
Very good. 44 microseconds. Check whether all of you have done with this or not.
Yes, sir.
Okay. And in different books, different types of philosophies or school of thoughts are given, right? But please try to understand these things. So whenever the switching has to take place, you will have no feedback, or sometimes positive feedback, where the positive feedback comes into picture, that we will see later, right? So now this zero crossing detector, whatever we have seen so far, right, that can be further modified into, okay, voltage level detector also. See here where we are going to go into lot many practical applications, right? So now for example, I will give you one simple example. When I give the example, probably that will make you more interesting. I have got a solar panel with me, modules, okay. I want to charge the battery using a charge controller or something like that, okay. So now my battery is a 12 volt battery. I just want to have the indication, right? Probably in most of the uh, chargers or the charge controllers, you have this kind of indicators, right? So whenever the voltage has gone below say 3 volts of your battery, it will indicate with a red light, okay. Then when you start charging that battery, right, there may be a blinking light, green light or something like that, right? So when the voltage level has gone above 9 volts, so that may indicate with some other yellow light or something like that. When the voltage level has gone to 12 volts, to which it is supposed to be charged, then it may indicate with some other color, right? So once it goes above that, due to some reason, of course there will be cutoff mechanisms. We have already seen the peak clippers and other things, right? So some cutoff mechanism, voltage regulation takes place, which doesn't allow the voltage to go beyond the stipulated value. However, due to some reason, if it goes like that, it will be indicated by some other lamp, some other LED. So these kind of things you can easily realize with the help of the operational amplifier circuit, right? Voltage level detector. Now the application of this ZCD is further extended to voltage level detector. So how does it happen now? Voltage level detector. See here, I draw the Opamp here. Again, the inverting type, the non-inverting type. I have connected this like this. This is plus VCC and this is minus VEE, and this happens to be your V0. Now I am giving the input here. So what I would do here is, okay, I take VCC here, and this is plus VCC. Let me call this as R1 and R2. So this is my VR2 now. this is VR2, right? So whenever your input crosses VR2, you get the switching. Earlier we had seen when the input crosses 0, or very strictly speaking 300 microvolts in that particular example, right? So then the output swing we are going to get, but here this VR2 is my reference now. So how would you get? Let us say you have something like this. Okay, here I would like to have this as my VR2. Okay, so now you can see I will take the swing here, something like this. Then maybe somewhere here I will have one more, something like this. So I take this color. Now you can see here, as long as the input is less than VR2, the output is yeah, here what I have to take is this check. So yeah, it should be taken like this. Am I right? Please check. Once the input goes beyond VR2, the output will go from minus V0 set to plus V0 set. Then it will go something like this. Then it will remain here, and again the swing takes place, something like this. So this is my VR2, and this is my plus V0 set, this is minus V0 set, this is T, something like this. You can think. Now if you vary that VR2 using a pot or something like that, so it is possible for us to get the output anywhere you want as per your requirement. It switches between plus V0 set and minus V0 set, right? So here the reference voltage now becomes VR2, right? When the input goes above VR2, so 1 second, I have made a mistake here. I have not shown the input value itself, right? So this is your V in. I am connecting V in here, and now since I am connecting V into the inverting terminal, okay, I will make the changes here only. This I will make minus, this I will make plus. Yeah, then now your circuit is correct. This is your V in and this is your V0. Otherwise, this waveform, if I connect this reference to non-inverting terminal and give the input to an inverting terminal, this waveform would have been the other way around, right? So it would have got inversion. Now this is fine. This is an example. Okay, we will see the different configurations as well later. So now as long as your V in goes above the reference voltage VR2, the output goes to the positive saturation, right? Whenever your V in goes below the reference voltage VR2, the output goes to the negative saturation. When V in is above VR2, V0 is equals to plus V0 set. When your V in is less than VR2, V0 is equals to minus V0 set. Now see here, earlier I had grounded one of the terminals. If you look here, if you look at the previous values, because my reference value was 0, now I am considering two values, right? One is the AC, which is given as the input, and another is the reference, which is the DC. So now the comparison between these two take place, and accordingly the output swings take place here, right? So more on these things we will discuss in our subsequent presentations.